Modern language models face a strict scaling imperative. To act as highly capable autonomous agents, they need to process contexts spanning 10 million tokens and route logic through multi-trillion parameter networks. The vanilla dense transformer cannot mathematically sustain this scaling. The big O compute limits are too severe. Looking at this standard block, the first bottleneck sits on the left, global softmax attention. Because every token must check its relationship against every other token, compute costs scale quadratically. If you double the sequence length, you quadruple the processing cost. The second bottleneck sits on the right, the dense feed-forward network, or MLP. In a standard setup, this is where the bulk of the model's parameters live. In a dense MLP, every single parameter fires for every single token. Your inference compute cost is strictly locked to your total parameter count. You cannot make the model smarter by adding parameters without simultaneously detonating your latency and compute budgets. Reconstructing the architecture for frontier scale requires mathematically bypassing the quadratic attention bottleneck and introducing conditional routing to bypass the MLP bottleneck. Scaling to trillions of parameters requires abandoning homogeneous computation in favor of selective, sparse architectures. This is the standard self-attention equation. The nonlinear softmax function here is the exact operation that forces the model to compute an enormous n-by-n interaction matrix. By deliberately discarding it, we gain the mathematical freedom to reorder the multiplication entirely. Without softmax, matrix multiplication is associative. We can shift the parentheses. Instead of multiplying the queries and keys together first, we multiply the transposed keys and the values. This reordering collapses the dimensionality. We bypass the n-by-n token interaction entirely. Instead, we compute the hidden dimensions against each other, shrinking an operation of millions of variables down to a fixed size of just a few thousand. What remains behaves exactly like a recurrent neural network. By multiplying keys and values left to right across the sequence, we accumulate a constant fixed-size state. Pure linear attention is efficient, but it is highly lossy. An unedited state vector carrying the entire context history forward eventually becomes noise. The network lacks a mechanism to forget irrelevant past tokens. To fix this, architectures like Mamba 2 and gated DeltaNet elaborate on the linear mechanism. They introduce input-dependent gates, represented here by gamma and beta. These gates do not rely on the prior hidden state. They look solely at the current input token to decide how much of the existing state should be carried forward and how much previous key information should be projected out and erased. Because these gates depend only on the input, they preserve an architectural duality. During training, the model computes the operations as massive, dense parallel matrices. At inference time, the model executes them as pure serial updates, carrying a fixed-size state forward without recalculating the past. Leveraging the associativity of multiplication converts a fatal quadratic memory constraint into a highly optimized parallel serial duality. If you want to retain the raw expressive power of softmax attention without the memory limits, the alternative is applying it selectively. This timeline represents a long context sequence, which we can process using sparse attention mechanisms, like DeepSeek's DSA. Before running full attention, a lightweight indexer scans the sequence in low precision. It calculates brute force inner products across the sequence to evaluate relevance. The indexer ranks those relevance scores and executes a top K selection, isolating only the tokens that actually matter for the current computation. Only this scattered subset of selected tokens is routed into the heavy, full-precision softmax attention block. Mathematically, the indexer's initial scan is still comparing every token against every other token. It remains an operation with quadratic big O complexity. The efficiency comes strictly from systems engineering. Because the indexer operates in a much lower dimension and at lower precision, its constant factors are minuscule. Optimizing these algorithms requires looking past pure theoretical complexity. By aggressively minimizing the operative constants on the front end, engineers make a mathematically quadratic operation behave practically like a linear one. With attention managed, we arrive at the second bottleneck, the dense feed-forward network. To scale up parameter capacity without exploding inference flops, we break the monolithic MLP apart into smaller, distinct subnetworks called experts. This is the mixture of experts, or MOE architecture. Instead of pushing data through every node in the network, tokens are routed to specific, specialized neural pathways. The router itself is extremely naive. It takes the input token and computes an inner product against a set of expert weight vectors. This outputs a probability mass, a score dictating which experts align best with the current token. Modern models default to token choice top K routing. The token independently selects a strictly capped number of its highest scoring experts, usually just 1 or 2, and ignores the rest. To push utilization further, architectures like DeepSeek segment those standard experts into dozens of highly fine-grained nodes. They isolate common language processing tasks into a single shared expert. Every token passes through this pathway automatically, preventing fine-grained experts from redundantly relearning basic syntax. The mixture of experts framework decouples latent knowledge capacity from active computational cost. You can train a model with hundreds of billions of parameters, but only pay the computational price of a fraction of them on any given forward pass. Training an MOE introduces a severe paradox. Sparse gating decisions are mathematically non-differentiable. Since we only activate a top K subset, the network never sees the loss gradients for the experts it didn't choose. You could treat this like a bandit problem and use reinforcement learning to teach the router, but the variance introduced by those algorithms makes the gradients far too unstable at this scale. Left to pure gradient descent, the model suffers from expert collapse. If one expert performs slightly better early in training, it receives stronger gradient signals. Its weights increase, making it more likely to be selected again. It creates a runaway feedback loop that funnels all tokens to a single expert, leaving the rest of the network totally dead. To prevent this, engineers inject a heuristic load balancing loss directly into the total modeling objective. This equation defines the balancing act. It multiplies Fi, the physical fraction of tokens assigned to a specific expert, by Pi, the total probability mass the router has allocated to that expert. Taking the derivative of this loss creates a direct penalty. The higher the fraction of tokens an expert receives, the stronger the negative gradient applied to its probability mass. It actively punishes popularity. In highly distributed environments, models apply this exact same heuristic loss at the device level, ensuring tokens are distributed evenly across the GPU cluster to maintain maximum hardware utilization. Achieving massive parameter scale requires overriding pure gradient descent. Without engineered heuristic losses forcing equitable distribution, the hardware simply starves. Frontier open models have moved past the homogeneous transformer design. This reconstructed architecture relies heavily on specialized pathways. It weaves state-space linear attention layers together with sparse dense attention to process million-token sequences efficiently. It deploys massive sparse parameter networks, kept stable strictly by heuristic load balancing losses, to drastically scale its knowledge capacity. Frontier optimization has transitioned into a discipline of low-level systems engineering. Architectural viability is now dictated by hardware-specific constraints, like communication topologies, cache memory overhead, and the manipulation of constant factors. By mathematically manipulating the matrix and enforcing selective execution, engineers have decoupled raw compute costs from sheer intelligence. If you want to keep exploring the math and systems powering these models, subscribe to the Learn by Doing with Stephen channel and check out the Stephen Data Talk podcast for more in-depth engineering breakdowns.